Hello and welcome to this calculus video. Today we will be talking about numerical methods.
Math 112.
So far we have developed a bunch of theory and tools to help us solve various kinds of problems. In many situations our final answer ends up being the value of a function at a point, such as e, or ln of 2, or the square root of 10. If you take these quantities and plug them into a calculator, then it will return a decimal representation to some number of decimal places. Your calculator does this by approximating values to a high degree of accuracy. In this video, we will see two methods that allow us to approximate values. The first method is the linear approximation. It is based on the observation that the tangent line to a function f of x at a point x equals a stays close to the graph of f of x as long as the values of x stay close to a. Therefore, the tangent line can be a reasonable approximation for values of f of x. The approximation is better for values close to the point of tangency. The formula for the linear approximation is that f of x approximately equals f of a plus f prime of a times x minus a. The right-hand side of this approximation is the function whose graph is the tangent line to f of x at x equals a, so it is sometimes called the linearization. L of x equals f of a plus f prime of a times x minus a. To use the linearization, we need the function to be differentiable at x equals a. It makes sense to use a linear approximation if the value of f of x and of its derivative is easy to compute at some value, but it is much more difficult to compute f of x for other values. A perfect example of this is the function f of x equals the square root of x. It is very easy to compute f of x exactly when x is a perfect square, but for any other value you might not even know where to start. Let's say we want to know the value of the square root of 10. As 10 is not a perfect square, we won't be able to compute it exactly. However, 9 is a perfect square, and 9 is close to 10. So if we linearize f of x at x equals 9, we get that the approximation f of x is approximately equal to 3 plus 1/6 times x minus 9. Plugging in x equals 10, we approximate the square root of 10 to be 3 plus a sixth, which is 3.166 recurring. Google gives the true value of the square root of 10 to be 3.162277 and so on, so our approximation isn't all that bad. The linear approximation allows us to approximate the value of certain functions. One way of thinking of this is that we are approximating the y value at some x value of interest. Another place where we may want to find an actual numerical answer is in solving an equation, such as cosine x equals x. We can always rearrange an equation that we want to solve into the form f of x equals 0. In the previous example, we could write it as cosine x minus x equals 0. Approximately solving this equation is finding the x value of f of x equals cosine x minus x for the y value of interest, 0. One foundational method, called the Newton-Raphson method or Newton's method, also uses the idea of approximating f of x by its tangent line. The idea is that we start by picking an initial guess, x1, to our root. We pick x1 using our best sketch, or guessing, or any other reasonable method. As before, we can approximate f of x by its tangent line at x equals x1, and the x-intercept of this tangent line, x2, is close to the x-intercept of f, as fx and the tangent line are close. This gives x2 as a refined approximation, and we can repeat this process linearizing at x2 and finding the x-intercept of the tangent line at x2 to give x3. We can keep repeating this process until we get bored. If you work through all the algebra, we find the formula xn plus 1 equals xn minus f of xn over f prime of xn. We can do an example where f of x equals x cubed minus 2x minus 5, and f prime of x equals 3x squared minus 2. If we choose x1 equal to 2 as our starting point, we find that x2 equals x1 minus f of x1 over f prime of x1, which is 2 minus f of 2 over f prime of 2, which turns out to be 2.1. Repeating this process another time, we find x3 equals 2.0946, and we could keep repeating if we need more accuracy. That's all for now, folks. Today we talked about the linear approximation to approximate the value of a function at a point, and the Newton-Raphson method for approximating the root of an equation.
Math 112.